Hello, okay, so I'm back with part 3. Let's talk about this scenario. So we have a wheel that is rotating clockwise, right? It's going this way, so it's clockwise. It's moving in the same direction as your clock, your, what do you call it? Hand clock? Yeah, it's moving in the same direction, which is going this way. So that's clockwise. Alright, so it moves from this angle to this angle. So this is your initial angular velocity and this is your final angular velocity. So it moves at an angular velocity and maybe it slows down or maybe it moves faster. Maybe the angular velocity is the same as the initial velocity. We don't know. Alright, so this is also your initial angle or theta naught, theta final. Okay, so theta final minus theta naught or theta initial is equal to delta theta, and omega final minus omega naught or omega initial is equal to delta omega. Okay, so that is your change in velocity and your change in angular displacement. So the initial time is Ti or T naught equals to 0, and then the time interval or delta T is equal to T final minus T initial. Assuming that the initial angular position is theta initial equals to 0, then the angular displacement is just theta final minus theta initial equals to theta, because this guy is a 0, right? So theta final minus theta initial is just theta, which is this dude over here. It's just that value, okay? Because we are assuming that it starts from 0, and if I reach 20 degrees over here, this guy is just 20 degrees. Same thing, okay? So that is just the convention for angular quantities. Okay, so rotation with constant angular acceleration. Previously, we talked about kinematic equation, whereby the equation is only valid if the acceleration is uniform. Same case here, we have kinematic equations for angular quantities, whereby the angular quantities are only valid if your angular acceleration is constant. Acceleration must be constant. Both kinematic equations, the acceleration must be uniform or constant. If they are not constant, you cannot use the kinematic equation, or you have to break it into parts. And we have discussed this before in kinematic equation for linear quantities. Alright. So angular acceleration, we know that it is the rate of change of angular velocity. So alpha is just change in omega over the change in time. And change in alpha is just this guy over here. This is final, this is initial. So rearranging this equation will give me alpha t, right? Assuming we start from time 0, so delta theta is just t final minus t initial. So this becomes a 0, so t final is just t, right? T final is just t. So that is how it's just t over here. So rearranging this equation, I get alpha t, this is the guy, and then I move this guy over here, gives me omega naught or omega initial plus alpha t. Does this look familiar? Yes, it should be, because it looks exactly like your linear kinematic equation, whereby we have v equals to u plus at. Sama, except that now it's angular. And then we also have average angular velocity, whereby this guy is supposed to be, the average is supposed to be delta theta over delta t, and assuming our initial theta is 0, our initial time is 0, that is how they come up with just theta over t. And then rearranging this gives me, I also have average omega written as initial angular velocity, initial omega plus final omega divided by 2. This also gives me average omega, right? So equating these two equations, so it gives me theta over here, and I want my t on this equation. So omega initial plus omega final divided by 2 times with t. So I just equated this guy with this guy, right? So it's theta t equals to omega t plus omega initial plus omega final divided by 2. Just rearranging this to over here. I get theta. Right? It's pretty simple. Okay, sama. Good. Okay, so this is your second kinematic equation. Does it look familiar? It should be, because it looks exactly like this guy. U plus V times T. Right? If you don't remember, then you don't know what to say because your exam is near. This is V equals to U plus AT. Okay? Alright, moving on. We have two angular kinematic equation. Next one. So using this guy over here that we already know, and this guy over here, this is our number 1, this is our number 2. Substitute 1 into 2 will give me, yes, this looks exactly like s equals to ut plus 1 over 2 at squared. So u, the initial velocity, is equivalent to your initial angular velocity, and s is equivalent to your angular displacement. Of course, acceleration is your equivalent. In the angular quantity world, the acceleration is your alpha, or angular acceleration. Time does not change anywhere. Time is always the same. Okay, that's something you need to take into consideration. Time does not change even though it's in angular or it is in linear world. Okay, so substituting 1 into 3 gives me, so it gives me v squared equals to u squared plus 2as. Ini salah. So this should be omega squared equals to omega initial squared plus 2 alpha theta. Okay, abaikan ini. Okay, so in your book it should be correct. Alright, next slide please. Okay, so these are your angular and this is your linear. So sama juga, this guy is velocity, initial angular velocity, initial velocity, alpha, acceleration, t, time. Okay, so sama, you just need to know that omega is v, alpha is acceleration, and theta is s. You just need to memorize the linear kinematic equation, convert it to angular. Okay, you don't have to memorize both.